Andrews.
Recording in progress.
All right. So the, of course, moment. I don't think that's funny anymore. Are we okay to like put it to rest after today? Poor Andrew. He probably has nightmares about us calling attention to his amazing voice. So, all right. Water balloon. When the latex is released. So what allows, of course, us to be dazzled by that image of the water still holding the spherical shape? Why? We wouldn't see that with gases, but we get to see that when it's liquid water. Because, so what is kind of the overarching theme that really, really, really is what sets apart liquids and solids? 2 words. We got it plenty of times yesterday, not surface tension, but the reasoning behind surface tension. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O. Particle attraction. Yeah. So that is, ladies and gentlemen, what, is really setting apart liquids and solids and why we study them together. All right. So on your packet, it has kind of an outline of our topics. Well, I know it doesn't look like we're making much headway, but in these topics, this is where I want us to be by the end of the day. So we are going to alternate kind of discussing stuff, applying that and answering questions, discussing a little bit more, applying, answering questions, and so on. All right, so could we first, and I know I asked you to do something for homework, but pause on that. So we reminded ourselves exactly, what sets apart solids, liquids, and gases. Okay. Kinetic molecular theory. Remember, there was a specific kinetic molecular theory for gases, and there were 5 parts, and it said, gas particles don't attract. When they collide, they have elastic collisions, et cetera, et cetera. We don't have that for liquids and solids, but of course, we're always approaching it with a kinetics approach. Anthony, what does the term kinetic involve? Yeah, and so we understand particles in motion are, the particles in matter are moving, and that motion has consequences. But the motion of liquids and solids is all based upon particle attraction. Okay, can I show us that we're going to tour through these slides, but also, if we page through our packet, your textbook does a bit of a, I'm going to say a lame job a little bit. No, it is a lame job with the text explanations of the different properties of liquids and so on. So I've provided some background so that it's here. I'm definitely thinking we might need like a little bit of a reminder of what London dispersion forces are, what makes it possible for dipole-dipole, and then hydrogen bonding. I'll ask you to do some questions for homework over the weekend that might involve that. So it's here to look at for a refresher on that, but also some more about our different properties of liquids. Okay, so we talked about, of course, surface tension yesterday. We talked about viscosity. All right, let's just make sure that we hit on everything. So, comparative to gases, liquids have very, very crazy high densities. So I'm on page 2 of your, student note packet. Very high density. And what's interesting about liquids is in amongst themselves, they have ranges of different densities. And remember, we've done it ourselves. And if you did the McMurray lesson, we know that oil and water do not mix because they have opposite chemistries, but they have such different enough densities that the oil will sit on top of the water. Now, well, actually, we could add other liquids, for example, acetone. Acetone is slightly more dense than water, but not less dense than water, but not as low as oil. So we could actually place acetone in between. So it's really neat. If you ever heard of a density column, you can stack different liquids. That's really, really unique. We can't really do that with gases for multiple reasons. Okay. There's no empty space in a liquid, so you cannot decrease its volume by pressurizing it, or in other words, it's incompressible. And liquids, of course, diffuse. Yeah. Excellent. Surface tension. And so last night at the dinner table, I'm sure, Dean, that, your nightly discussion of, all right, what did you do in chemistry class, or teach us what you learned in chemistry? And you brought up surface tension, and your mom or dad said, wait, can you remind us what is surface tension? And you, of course, said, don't read. How does the surface get tight? Surface tension. We only see it with liquids. All right, in a liquid, if we can, get on that Miss Frizzle school bus and go into the liquid and imagine we can view the water molecules. All right, well, they're attracting each other. They're pulling on each other. But what about the surface? I'm going to ask Luke to step in. Go.
Does it pull like from side to side and then like up and down?
Up?
Or
well, if it's in the liquid, yes, but at the surface. Are the ones at the surface being pulled up?
just side to side?
Yeah, side to side, but also downward. So it kind of is like an angled overall pull. And what that allows is a strengthening of the surface. And so we can support weight that we normally shouldn't. Yay! My heart is overflowing with happiness that you're here. And so that's what we saw yesterday, Dean, whenever we put a podium powder on and then the drop of soap got between the water molecules, so they couldn't do that. All right. If we place a tube into a liquid, now, of course, it depends on what is the identity of the liquid and what is the tube made of. But have you ever noticed that when you use a straw, we know how a straw operates, but if you use a straw, if you look inside the straw, often the liquid moves up a little bit inside. I don't know if we've ever noticed that. That's called capillary action. As long as the molecules of the liquid are attracted to the molecules of the cylinder, what happens is, of course, they're pulling sideways and downward, but they'll be attracted and actually be able to climb upon each other. That's the reason we form a meniscus, but that also causes the liquid, and the narrower the tube, the higher the movement. Sequoia trees are the largest living organism in the world. Yeah. I don't know if you've ever gotten to see in person, like the General Sherman tree. Sherman? So there's the giant sequoia forests in California. Those are the largest living organism because they're massive in width, also height, but the tallest trees are also California. Redwoods. And it is truly hard when you're, within a couple of feet or so to look up and see the top. I mean, they are just So statuesque, if you will. Now we know that nutrients need to get up to nurture the tree. Well, how do nutrients and water? Through capillary action. You guys know this, yeah? And so, you know, trees, how do they get to the tippy top? You know, the nutrients for the leaves and so on. Well, capillary action. Yeah, there's small channels, straws, if you will, veins that allow the movement, and it's all because of particle attraction. Capillary action. But that also describes why, you know, we often use paper towels to clean up our spills. There's complementary chemistries. You don't have to necessarily run the paper towel through the spill. You can just set it on it. And we know the liquid will move through the material. That's another version of capillary action. Okay, different liquids pour at different speeds. You lucky ducks have always had the blessing of plastic ketchup containers that you may squeeze and use pressure to help get the very viscous ketchup onto your hamburger, hot dog, etc. I'm sure your parents have shared with you, or maybe your grandparents. Our ketchup was always in the glass bottle, and there were all kinds of strategies. You would take the lid off, hold the glass bottle at a 45-degree angle, and you would hit where the pickle is on the hind side. So silly. And sometimes, you know, you have several glass bottles and try to race who could get the ketchup out the fastest. Ketchup is a very viscous liquid, much more viscous than water. Honey is more viscous than water. Viscosity is resistance to flow. Resistance to flow. So Roman, what would cause, so we understand that the particles in a liquid are exchanging places. So if you're pouring a liquid, what would hold it back? Why not? Now, of course, it's not that they want, but they're sticking together because why? Yeah. Because of particle attraction. So the greater the particle attraction, the more sticky, the more they're resistant to exchanging places. Well, oobleck, we could say, has a high well, and it's all like relative. We actually have a way of measuring viscosity. You have like you measure the height of your liquid, and then you drop a certain weight of a ball bearing, and you time how long it takes for it to fall. So like different motor oils. I don't know, probably haven't had to buy or replace the oil in a car yet. Anyway, like, you know, 10W30 something. They get different ratings based upon their viscosity. Oobleck. So yeah, compared to water, much more viscous. Now remember, oobleck though, that is a Newtonian fluid. So it's like this like strange being all its own, but overall we would classify it as being a liquid for sure. Much more than a solid. So, but there's other things too that can lead to something being more viscous. So of course, the stronger the particle attraction, but also they could just be long molecules. And so as they're trying to exchange places, they get tangled in each other. So I mean, there's other possible factors, but it's really up to the particle attraction. Did that answer? Yeah, that's a really, really viscous liquid.
Would honey be less dense than water then?
No, I think honey is definitely more dense than water. But it's a little tricky because it's soluble in water. But yeah, I could just think, I don't know. I think whenever I add my honey to my cup of tea, it definitely sinks to the bottom, but then eventually dissolves. why would you say it's less dense than water?
Just because the particle attraction is higher.
So do you think particle attraction is necessarily tied to density?
Yeah, that's what I thought.
Well, do you think the greater the particle attraction, the less dense?
Yeah.
Why?
It's like closer to a gas, which is like not as dense.
Yeah, I mean, liquids and then gases. So if you have 1 milliliter of liquid, it'll be about 1,000 milliliters on average. So gases are 1,000 times less dense than their liquid counterpart. But wouldn't you say the stronger the particle attraction, the more those particles can hold each other close? Or can just hold each other. But I think it also has to do with the shape of the molecule and the size. Because water, hydrogen bonding, it has a much higher particle attraction than honey, but honey molecules, they have high particle attraction and they're big and they get tangled when you pour them. So they have both of those factors. I think particle attraction plays a role in density, but it's not the sole determiner. Go ahead, Abby.
Like particle attraction, more particle attraction also sort of gives more mass because it's not going to break out in the water.
Yeah, yes. And so that depends on that as well. Yes is yes. Go ahead.
Why don't you like heat up honey and like run?
I know. Well, I just laugh because I remember my kids were young and we went to IHOP. And then I haven't been to IHOP in years and years and years. But when I took my kids this one day, I remember they brought the syrup to the table. And I just quickly, as the mom, went to put a little bit of syrup on their pancakes. And before I knew it, oh my gosh, the whole plate was filled with syrup because they heat their syrup. And temperature is directly related to kinetic energy. So we're giving the particles more energy that they can use. So where they would get tangled, well, you're giving them more energy to overcome the tangled or whatever else. Yeah, so viscosity can definitely be impacted by the temperature of it. Yeah. All right. Page 23, please. Page 23. So can we, I don't know, apply or kind of measure our understanding of these properties of liquids? So mainly particle attraction is what these questions will ask us. So could I please ask us, let's take like 2 minutes and choose the best answer for 5, 6, 7, 9, and 11. Before you dig in, we see the terms effective several times, effective. So using in a sentence, eating a bowl of oatmeal for breakfast is more effective at keeping you full than a single Skittle. So effective, what is doing the job better? Okay. Do you see your page? It was like 30 more seconds. Okay. So would you feel comfortable for number 5, sharing what you chose?
Oh, I skipped one, sorry.
Oh, no problem. So can I come back to you?
Yeah.
No problem. Yeah, that's okay. Sophia, do you mind sharing? What did you choose for 5? I agree wholeheartedly. Now remember, a water molecule always has attraction for another water molecule, just is it showing itself or not? And so it's the kinetic energy in reference to, so it's present in both the liquid and the gaseous state, but it's showing itself. Okay. Let's see, Julia. Oh, should I go to Zoe for 6? Okay. Do you feel okay with 6?
Yeah, I got C.
Agreed. So Julia, how about 7? I agree very, very much. B for 7. So we have D for 5, C for 6, B for 7, 9, C, 11, B. Questions? All right. So, Aaron, question for you, sir. Could you complete these for me? Okay. The stronger the particle attraction between molecules of the substance, the greater the surface tension, the lesser the surface tension. Keep going. The stronger the particle attraction, the greater or the lesser the capillary action. And we would be moving forward with the understanding that the walls of the vessel are of complementary makeup to the liquid. Yeah. Now, of course, the wider the cylinder, we're not going to see as dramatic of a meniscus in essence, but we would just be talking about, that being constant. We're looking at different liquids. So you're right.
Is that like help? Like, because sap is like not as fluid as water. Does it like help bring it up?
Well, see, is it the sap, if I'm not mistaken? Oh my gosh, please correct me on this, because I am not like arborist, So like when you tap a maple tree for maple syrup, you tap it whenever what's been stored in the limbs is now running back down. And that is a certain time of year, like whenever we're no longer freezing temperature and that kind of thing. And it's running in this direction. That's why you can then have it run into your vessels. But then, so is it just what? I don't know. So like the sap, like pine trees, but all trees have it. So is it just that fluid that's running in those channels? Wait, what was your question again? Like,
Does it help with the capillary action?
oh, it depends on the attraction of that material to the walls of the container. So I would think, because capillary action officially is movement of a liquid up a narrow tube against gravity. So you think the thicker it is, the harder, because it's having to combat the pull of gravity? I don't know. What do you guys think of that? That's a great question. Is the sap just what's the nutrients are running in, right? Like blood is to a human being as sap is to a tree. Or am I wrong on that? Is sap something different? And I'm embarrassed that I don't know. Anybody know that? I think we have to, I guess, find out because I feel. I don't know. Yeah. I'll try to find an answer for us. So Roman, am I okay, Aaron, to volley it over? Okay, so one more. The stronger the particle attraction, the greater or the lesser the viscosity.
What's that? Yeah.
What you're talking about, kind of. So sap,
I thought that was capillary action. I was talking about.
it was. But they're all related because of particle attraction. So viscosity is resistance to flowing.
It'd be the greater the.
Yes. Okay. So if we turn to what is the typed page 4, type page 4. Okay, any other comments, questions, concerns? I invite, or yeah, I don't know. Chemistry is my specialty. I guess that's the chemistry of the tree though. Oh, shoot. Oh, I'll get an answer for us. Okay, so we know what makes a solid is the particle attraction is truly showing itself and is limiting, of course, the volume and the shape. Definite volume, definite shape. We can, of course, take a solid and create a liquid from it through melting. We'll talk more about phase changes on Monday. They also have a high density and not the dramatic difference that we saw from gases to liquids, but where it's 1,000 times a change of density from a gas to a liquid, it's only about 10 times from a liquid to a solid. They also cannot be compressed, no empty space. All right, solids. Because we observe it, we need to reference that it's possible. Now, as you sit in your seat, gosh, again, so sorry. All right. Are particles from your pants, shorts, skirts migrating into the seat and then vice versa? Isn't that diffusion, right? The spontaneous mixing of two fluids due to their rapid random motion. Well, if that's how we define that it has to be a fluid, solids are not fluids. Remember, to be fluid, that means the particles are exchanging places. How can we have diffusion? Very, very slowly. And we only see diffusion with solids whenever we have two solids, usually a very complementary makeup, like two metals that are made of atoms about the same size that are pressured together. So for example, maybe parts of a bridge. A metal is secured to another piece of metal with a really tightened screw. So they're being held together with a lot of pressure. And then some, we think, as they vibrate and rotate, are exchanging positions. And then with pressure, exchanging position, and so on and so on. So because we see it, we do say they have very, very slow rates of diffusion, but not enough to make them classified as fluids. So no, you are not losing particles of your pants or your shorts or whatever else into the seat and vice versa. Okay, two types of solids. So solids can be grouped to either be crystalline or amorphous. So if you turn the page. Okay, so here's a bit more, but I think what will help the best are the photo or the images that I have on page 24. Page 24. Okay, so if we gather a bunch of solids from the room, we could make two separate piles. One, the solids that are crystalline, and the other that are amorphous. So to help us to know what is what, I have several samples. So I have two geodes. I'm not sure of the origin of these. And if you want to pass these around. And then these are two samples of quartz. And so I don't know about you, but when I think of crystal, I think of gemstones. But actually the majority of solids in our world are crystalline. So what makes a crystal a crystal? What do we observe? They're kind of sparkly, pointy. They have like they're sparkly because kind of they have flat faces that are reflecting light. And when I look at the crystals, they're similar in their shape. Yeah. So what makes a crystal a crystal? I know I've said this before, not sure if we've observed salt crystals that come out of our salt shaker. How about sugar, granulated sugar crystals? Do you ever look closely at their shape? Right. Have you ever examined or taken a look? Are they in the shape of a heart, a star, a rainbow? I don't know. Yeah. So I think we can realize no. They naturally are cubes. Have you ever looked at granulated sugar? I think we need to take a look at granulated sugar or I don't know. I know I have showed you before. Can you see? This is pretty fine grit. I don't know. Can you see, Trey? Can you? Tiny cubes. And Trey, if you put some of the crystals between your fingers, if you press, now it's hard because we're not like measuring, but you actually end up grinding them, but they're still cubes and really hard to see with how small they originally began. A salt block. So I know that where I grew up, there were a lot of farms, a lot of fields. And so in the wintertime, either a farmer or sometimes just a good Samaritan would put a salt block for the deer, and for sometimes you can use a salt block for cows. In the wintertime, that gives them a source of nutrients, but also they'll lick it and they get thirsty, so they're drinking enough water. Have you ever seen a salt lick that you might put out? It's a big cube. It's a big cube. So let's just say in my neighborhood in Bethel Park, I'm going to put a salt lick out for all the deer. And so bring a salt lick and give them a Tractor Supply store. Imagine me carrying that cube, and clumsy Mrs. Gerhardt is going to drop it. And if I would drop that cube, it will break into smaller cubes and break into smaller cubes. Dean, are you writing on my quartz? So you're poking at the cups? So you're just exploring. All right.
He's like one of those dinosaurs.
Okay, now I must say, what lead in your pencil? That's the common name. It's not lead. It's not PB. Graphite, which is another common name. What element do you write with? Carbon. Yeah, sure. We're in chemistry. Don't call it pencil lead. Yeah.
Wait, what's the thing Trey did?
Oh, just took salt and crushed it. Okay, stay with me, stay with me. Okay, what makes a crystal a crystal? So why would we take that salt lick and it would break into smaller pieces? Okay, even if you've never played with Legos, we can imagine this. So we know Legos come in all shapes and sizes. So let's say we had a bunch of just cubic Legos. Well, if we put those cubes together, we would just get a bigger cube. And then what if we put those together? We just get a bigger cube. So that is what Trey was holding, a larger cube of salt that with force, he was making smaller and then smaller and smaller, and eventually would get what we would call a unit cell. A unit cell, and this is sodium chloride, where the dark spheres are the sodium ions, and then the white are the chloride. Well, we could never see this with the naked eye. It is many and many and many of these stacked, and many and many, many more, and many, many, many more that eventually create what we call a crystal lattice. Whoop. So crystals are made of unit cells. A crystal has a regular repeating pattern to its structure. Amorphous. Amorphous, they don't have any organization to how the particles are arranged. For example, now carbon we can find as diamond, graphite, or soot. So if you are burning a log and the black residue, or a marshmallow and you catch it aflame and it's all the black kind of sooty, carbon in the form of soot is amorphous. There's one carbon maybe joined to carbon here, this one over here. There's not a repeating organization. So amorphous, there's no organization to the structure. The majority of our world, even though we don't see gemstones on the particle level, it is. So the majority of our world are crystals. Okay, could I ask you for homework to please answer the questions? And I know whenever I say it, it'll seem like, oh my gosh, so much homework. It might take you 10 minutes, maybe. So I know that we did properties. Yikes. Could we please answer the questions on 18, 19, and 20? 18, 19, and 20. Again, maybe 10 minutes of time. Okay, we will continue onward Monday. 18, 19, and 20. Bless you.